Click the bell icon to get latest videos from Ekeeda.
Hello friends, we have seen how to solve linear partial differential equation using the method of grouping, where we found the auxiliary equation and grouped them to get the final general solution. In this example of this video, we will see the second type of solution using method of multipliers. We have seen how to solve a linear partial differential equation of Lagrange's form and how to get we have seen how to solve a linear partial differential equation of Lagrange's form in the earlier example. There we used the method of grouping. Now we will see how to use the method of multipliers. Let us start with the linear partial differential equation of Lagrange's form. The basic form of this equation is, this is our required equation in the required form. The auxiliary equation to solve this is, now, as I said, the first method of grouping, where we group any two from this auxiliary equation to get the solution. The second method that we will be seeing now is method of multipliers. Now, for method of multipliers, this particular method is used and it comes into play only when grouping doesn't work. That is, even if we group two parts, we are not able to integrate them easily. In such a condition, we'll use the method of multipliers. Let us say we take the multipliers as, so let L, M, N be the three multipliers. Then we will get a fourth part for the auxiliary equation as follows. So we select the values of multipliers L, M and N such that we get the fourth part for our auxiliary equation. The fourth part will be L dx plus M dy plus N dz whole upon PL plus QM plus RN. Now, how do we actually select the values for L, M and N? What should be the multipliers? That will depend upon, rather, we should select multipliers in such a way that the denominator PL plus QM plus RN should either become 0, that is, it should either become 0 or it should be such a simple thing that if we group it with any of the earlier three parts of auxiliary equations, we will be easily able to integrate it and find the solutions. Correct? So the selection of the multipliers is an important step of solving our given linear differential equation with the help of auxiliary equation with the help of the multipliers L, M and N. Let us take one example to understand the use of multipliers. Let us take our second example of solving linear partial differential equation of Lagrange's type. This is our given linear partial differential equation. This is in the Lagrange's form. So the given equation, comparing to our standard form, we get P is equal to x square minus y square minus z square. Similarly, and so we get Q as equal to and R as equal to. Now we will be forming our auxiliary equation. The auxiliary equation is given by, so this is our auxiliary equation given by dx upon p is equal to dy upon q is equal to dz upon r. Let us substitute the values of p, q and r and get our auxiliary equation for this linear equation. So we have, this is our equation number 2, and our question, that is the given linear partial differential equation, will be our equation number 1. Now, as we all know, we'll be solving the auxiliary equation to get the solution of our given linear partial differential equation. Now, the first method was method of grouping. So, which two parts can we group to get our first part of the solution? We see that the second and the third part we can group easily. We'll cancel out 2x and we'll be able to integrate easily. Let us start doing that. Therefore, we will be left with integrating this, we'll be getting our first part of the solution. Integrating this particular part, what we get is therefore further simplifying this, we'll be getting the actual first part of our solution. So this is our first part of the solution that we have got, that is y by z is equal to a. Now let us rewrite our auxiliary equation and see if we can group any other two parts to get the second part of the solution. So our auxiliary equation is this was our second equation, auxiliary equation. We had grouped second part and third part to get this part of the solution. Now, can we group first part with any of the other two? Can we group dx upon x square minus y square minus z square with any of the other two? Even if we group that, we will not be able to solve it properly. We will not be able to cancel out anything and integrate it further. This is when the method of multipliers comes into picture. Now, as I said, we have to select 3 multipliers where we will be able to make the fourth part's denominator as equal to 0 or as simple as possible. Now here you will have to students do trial and error method. You will have to check what multipliers to be used. Let us take few multipliers. Let us say let us do trial and error method. We can assume any of the groups, say 1, 1, 1 or x, y, z, or say minus 1, minus 1, minus 1 to be the multipliers. We can use any of them. In this particular case, we'll check what helps us solve this equation better. If we put 1, 1, 1, this is not going to make any difference. If we put minus 1, minus 1, minus 1, we multiply this denominator, this and this with minus 1. Again, it is not going to make any difference. But if we multiply these three with x, y, and z, what do we get? Let us check. This is what we get when we multiply the first denominator by x, the second denominator by y, and the third denominator by z, and we add the three of them, we'll be getting this. And if we simplify this further, we see that minus xy square plus 2xy square will give me plus xy square, minus xz square plus 2xz square will give me plus xz square. We can take something common. Let us see what we get. So this is what we get when we simplify the denominator further after multiplying the multipliers x, y, z to the three parts of the auxiliary equation. So if we simplify this and we check with our auxiliary equation, we'll be able to integrate it easily. Let us do that. Let us put this as our multipliers, that is x, y, and z. Let us rewrite the auxiliary equation first and then use the multipliers. This was our auxiliary equation. Let us use the multipliers x, y, z. What we get as the fourth part is we have L dx plus M dy plus N dz. So our L, M, N are x, y, z. So x dx plus y dy plus z dz. Whole upon we had P into L plus Q into second part and plus R into third part. So P into first part is X. What is our P? This is our p. So we'll multiply this with x. We'll be getting x cube minus xy square minus xz square. When we multiply the second part, q with y, we'll be getting 2xy square. When we multiply the third part with z, we'll be getting 2xz square. And simplifying this further, we finally get x into this bracket as our denominator. Let us directly write this as our denominator. Now, friends, if we compare, if we differentiate the denominator, if we use the derivative of the denominator, we'll be getting the numerator, correct? 2x plus 2y plus 2z, we'll be getting the numerator. So let us start integrating this. Let us club this with any of the second or the third part so that we can get the 2x as cancelled. Let us club this with second or the third part so that we can get x cancelled and integrate this further. So clubbing, let's say 2 with 4. So we have grouped together the second part and the fourth part. We'll be cancelling out x. What we are left with is dy upon 2y. And what here we are left with is x dx plus y dy plus z dy upon x square plus y square plus z square. And we know that derivative of this part of the denominator is equal to the numerator, correct? We only require a 2 to be taken and adjusted in the numerator, and so we do that also in the denominator. So what I can write is 2 in the numerator and 2 in the denominator. So adjusted 2 over here, the denominator 2 from right hand side and left hand side will get cancelled. On integrating the left hand side, we will get log y. On integrating the right hand side also, since we have the derivative of the denominator in the numerator, we will be getting log of the denominator. Let us write that answer and find the second part of the solution. So this is what we get after integrating. Let us simplify this further and get the second part of the solution. So this is our second part of the solution, and combining the first and second part, we'll be getting our final solution for the given partial differential equation. So let us rewrite the first and the second part of the solution. The first and the second part of the solution will be therefore our final general solution will be in the form of, which can also be written as this is our final general form of the given partial differential equation. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.